which suggests we're done. Unless you want to take it one more step and rewrite it as k plus 1 plus 1. But I think at this point we're probably good. Questions, comments, sharing?
Really clever. Oh no, just Gauss. He had a really clever argument, and he basically like paired out like 1 and k plus 1, 2 and k, and then 3 and k.
That's the example. Yeah, when you look up and read about this stuff, right? The classic example is, what was he, a grade school student?
Yeah, like,
and the teacher was like, yeah, we're going to keep you busy, young man. Go ahead and add up the numbers from 1 to 100, thinking, you know, I'll buy myself 10, 20 minutes, whatever it would take you to add up all those numbers. Dude's like, well, 1 and 99 make 100, right? 2 and 98 make 100, and he got this, you know, did it real quick down there. Yeah, and it's funny because that's in all the articles when you look at the triangular number proof. And they're like, and Gauss did this way back in the day. Anyway, there you go. There's our first proof by induction. To review. I'm going to keep doing this for you, John.
This might be the last time we.
Filming it.
This will be the last time we do.
First thing we need is we need a statement to be proven, so we know where we need to land. We always need that anchor step, right? The base case is typically how I refer to it. Then we have the inductive step, which is really about two things: assuming the hypothesis when n equals k, right? So this is assume that n equals k produces a true statement, and then using that to show that the k plus first statement had to be true. So I think it's simply you'll take the left-hand side, mess around with it, using our hypothesis until you produce the result. There you go. Let's do another one and see if it's still fun. This is a pattern that most people have probably noticed in one form or another. Anyone ever noticed that before? You add 1 and 3, you get 4, which is a perfect square, 2 squared. You add 1, 3, and 5, you get 9. 9, of course, is a perfect square, and so on, right? You've seen that pattern? You're nodding? I'm certain you have. How many of you ever looked at a table of values for y equals x squared? And you ever notice on the right-hand side that it goes up 1, up 3, up 1, right? I mean, that's basically what we're seeing, is that pattern that you've seen in the quadratic. And it has another fancy name? It's nice. It's cute. It's cute. That's not a very fancy name. But anyway, right, what we've got is the first odd number is 1 squared. The first 2 odd numbers added together gives us 2 squared. The first 3 odd numbers give us 3 squared. The first 4 odd numbers give us 4 squared. So it appears as though the sum of the first n odd integers is equal to the nth square, right? That's a way to state the pattern a little more formally. So here you go. This is what we're going to try and prove. So odd numbers are always one more, exactly. They're one more or less than an even number, right? Have to be, right? Even odd, even odd, even odd. So a way to describe the first odd number is 2 minus 1. The second odd number is 4 minus 1. The third odd number is 5 minus 1, right? So I want everyone to be clear. That's what we're talking about here. The 2n minus 1 is the nth odd number. So that's going to be our statement to be proven. Now, let's see if you can fill in a base case. That'll buy me a second to put this up on the board. That. Plus first, keep that. So, base case, did it work? Thumbs up or not? Ryan, you're nodding affirmatively. What'd you write on the page that said the base case works? That's what you wrote. That's something we can all be pretty comfortable with. You'll notice that the base case is true. quite often pretty straightforward. Right? Nothing too fancy about that, it's just pushing the first domino. So what would our inductive hypothesis say? We're going to assume that this statement is true when the n value is k.
I'm just going to substitute k in for n.
Just got the hang of it. Whoops, and I better write the darn thing correctly. Plus 2k, take away 1, must be equal to k squared. That is a true statement for our purposes right now. Now what we need to do is write the k plus first statement, see what happens. So, what would the k plus first statement be?
2k. 2k plus 1.
No, 2k plus 1.
What's the next odd number?
2k plus 1.
Right, 2k plus 1. We'll highlight that. And what would that have to be equal to?
3k plus 1 minus 1. 2 times 2.
What are we subbing in the k plus first statement?
K plus 1 squared.
So we have to sub in the k plus 1 value. There you go.
Should that last orange one be 2k plus 1 minus 1, or does that matter?
That's the same thing. It'd be the
That's
same.
what I was just thinking, Tom. Which of course simplifies to
2k.
2k plus 1.
right. So either or.
Okay.
Right. We're there either way, but we sort of did. I sort of jumped over that sub in k plus 1.
Okay.
But of course recognize that this is just. Right. So either way we're good. All right. So what are we going to do? Rhymes with take the left hand side and play with it.
Take the left-hand side and play with it.
Let's take the left hand side and see what we can do. Keeping squishy intact.
Squishy squish.
So what do we got? 1, 3, 5. Right? That's our left-hand side. All right, what does the inductive hypothesis tell us?
So everything before that last one equals. Yeah.
So let's do that. Agreed? Quick question, Keith, do those parentheses really do anything for you? Not really, right? So I see no reason we can't get rid of them. What was the F word?
Factor.
We could factor a quadratic. I know, I'm sorry, we don't do that very much. But you could always think about it as, well, what are the horizontal intercepts? There's 2 of them, they're minus 1, that gives you a linear factor of x plus 1, so that you plug formula twice, blah, 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 blah. And you could FOIL that out, k plus 1, and verify that it actually works. Right? So, what have we done? Yeah, we've proven that the k statement forces the k plus first statement to be true. Therefore, what's true? Sum of n odd integers has to be equivalent to n squared. Which is kind of cool. I thought it was kind of cool.
I think it's awesome.
You want to spin that around while you do the perimeter one more time?
Spacing up, sorry.
Keep busy, John. All right. Let's do another one. I'm just going to let you guys play with this. 4n minus 4.